This video will be about machine instructions. Now, machine instructions can take on various different formats depending on the exact architecture you're using. But in general, all machine instructions have an opcode, which is followed by some number of operands. Now keep in mind that the number of operands can vary, even within a particular instruction set. The x86 instruction set in particular is very complicated and has instructions with varying numbers of operands depending on the instruction. Operands are also sometimes called addresses, and this is true even if we are not talking about memory addresses. It is true that many machine instructions do refer to memory addresses, but they also refer to things like registers and even hard-coded numbers. But these are all called different types of addresses, and different addressing modes will be discussed in a future video. For now, we'll simply consider what the machine instructions of a system look like when you have a particular number of operands. So we'll be making up some relatively simple and clean machine instruction languages that have a uniform number of operands, like so. In these simple examples, most of our instructions will be arithmetic operations of this form. Although computers do more than simply add, subtract, etc., that is a big chunk of what they're capable of doing. So we have, in this case, 3 operands. Y is taking on the result of adding A and B. So this would be something we can represent with instructions that have 3 operands. Now, although this video is about machine instructions, what I've actually shown here on the right are assembly instructions. The machine instructions would be binary representations of these commands, where each of these mnemonics would have a corresponding opcode represented by some fixed number of bits, at least fixed for our simple examples that you'll be seeing in this video. But each of these instructions is the same. The first operand is always the destination of the operation, and the next 2 operands are the 2, what we would say, traditional operands in an arithmetic sense to these specific arithmetic operations. But what do we do if we are restricted to only 2 operands? We would get a result that looks like this. In order to transition to 2 operands, we're going to remove the destination operand from our assembly instructions. But that means that we can't use Y over here. But we still need to store our results somewhere. So what we'll do is simply use the first operand in each of these commands as both an operand of the actual arithmetic operation and the destination of the computation. Now, all of these assembly instructions have 2 operands, but they are still able to compute an arithmetic result and store the result somewhere. But we have to have caution now because we will overwrite whatever the original result in the first operand was. Because of this, when we are using 2 operand instructions, it becomes necessary to have an additional instruction called move. Despite this common mnemonic, which appears in many assembly languages, a more fitting name would probably be copy, because what this instruction does is it copies this operand into the first operand, as shown here. You could have such an instruction in a 3 operand language as well, but you would be ignoring 1 operand slot, and generally you wouldn't need it. In this language, we absolutely need it because we want to sometimes maintain copies of values that would otherwise be overwritten by the arithmetic operations. Despite overriding one of the source operands, these 2 operand instructions are still fairly easy for a human to use in programs. However, it is also possible to have an entire instruction set where all of these operations consist of only 1 operand. However, perhaps it is more accurate to say that there is going to be 1 explicit operand and then another implicit operand. all of our instructions will still have the form A taking on the value of A and then some arithmetic operator applied to B. So I will remove A from all of these assembly instructions. So now each of our instructions only specifies a single operand, but all of our interpretations of what these instructions do have A and B. So what is A here? Well, it's a special register known as an accumulator. And to make that distinction clear, I will label it as such on the left side here. Because the accumulator is a special register reserved for this special purpose, we can save space in our machine instructions by not specifying it over and over again. However, this adds complexity when writing programs, as we'll see in a moment. But before we can write complete programs, we actually have to add one additional instruction. Notice that this move operation can put a value into the accumulator, but we don't have a way of getting a value out of the accumulator. What we need is an additional instruction that puts the value from the accumulator into a register of our choosing, in this case designated by B. So this will be called a store operation. And because this operation stores a value into a chosen register, it is common to call this move operation load. So load will put a value into the accumulator, and store will take a value out of it and put it wherever you like. Now we have a complete instruction set that can write general programs with one operand instructions. But it is possible to go even further and create a complete instruction set where each of the instructions has 0 operands. So how would we do this? Well, I'm going to remove all of these operands. I'm also going to remove these operations and completely change how everything works on this side. So now we have a completely new notation using the symbols top and second. What do these refer to? These 0 operand instructions will make use of a data structure called a stack. Top refers to the top element of an implicit stack, and second refers to the second element down of an implicit stack. Now technically with a stack you're only supposed to ever access the top element, and when we are using the stack this will be the only element we really ever access because we will only ever access the second element down immediately after popping off the first element. Let me show an example of how this works. Let's say that a stack has the values 5 and 4 on it. So 5 is the top of the stack and 4 is the second element down from the top. There could be more elements, but they'll be irrelevant for this example. If I execute a subtract operation, then I will pop off the 5 and pop off the 4, compute the result 4 minus 5 to get a result of -1, and then push that value back on top of the stack. That is how all of these operations work. There is an implicit stack, and when one of these arithmetic operations is executed, we will pop 2 elements off, perform the corresponding operation, and then push the result back on top of the stack. Now note that the order of the operands is particularly important for division and subtraction. Because of the use of the stack, all of these instructions require 0 operands. However, to actually get elements on the stack, we do require some simple operations that take a single operand, namely push and pop. The push operation takes a designated operand, in this case B, and makes it the new top of the stack, pushing everything else down. The pop operation will take the top off of the stack and store that element into B. Now usually when we have this backwards arrow, we're really copying a value, but in the case of these two operations, we really are modifying the stack. The push makes B be the top element, and the previous top is now one position down. And the pop operation will actually remove the top from the stack so that a different element will be the top, assuming there are any left at all. So now, with these operations, we can write complete programs. And in fact, we will write complete programs using all of these sets of instructions to show how they compare and contrast. This is the arithmetic result that we'll be calculating with each of our different instruction sets. Let's first compute it using machine instructions that all have 3 operands. In this case, the program is relatively straightforward, and there are several ways of doing this, but I will choose to multiply, saving the result in y. I'm going to multiply a times b. So at this point, y equals a times b. Those are the original values of a and b. And then I will add d and c and store the result in d. So note that I'll be overwriting the value of d. I could have put this in some other temporary variable perhaps, but I'm assuming it's okay to overwrite the values I have. So at this point, d equals the original values of d plus c. Then I will do division, and I will also store that result in d. And note that because at this point d equals the original d plus c, that after that operation d will be the result of d plus c quantity divided by e, which is this portion of the expression. And then at the end I can do subtract, and because this will be the last step, I will store this result in y, and my other operands will be y and d, keeping in mind that at this point the value in y is actually a times b, and the value in d is actually d plus c divided by e. So after this operation, y will equal a times b minus this whole quantity here, which is exactly what we were trying to compute up there. So when using instructions with 3 operands, the program is relatively short. There is some redundancy here. We didn't really need 3 operands for the most part, but we did save a step or two, as we'll see in a moment. However, although the number of instructions is only 4, the length of these instructions in terms of bits is going to be longer because we're specifying more operands. So that's something that you can only see behind the scenes if you look at the actual binary. So let's repeat this using 2 operands for each instruction. So in this case, we will have a fairly similar program. We'll start by multiplying a and b. In this case, a will store the original a multiplied by b. Once again, I'm assuming it's okay to overwrite the original values. Then we will add. So in this case, d takes on the original d plus the original c. Then divide. And at this point, d already contains d plus c, so the result that we'll store after this will be d plus c divided by e, and so that is this portion of the expression. And then we can do a subtraction, and this puts the value into a of a times b, because this is what was in a at this point, minus this whole quantity. And this is the result we want, but it's in the wrong variable. We need to store it in y. And so we actually will use our move instruction to move a value into y from a. And so now y equals that expression, and we are done. So these two programs were relatively straightforward. Things get more complicated when we have instructions with a single operand. We really have to think carefully about the order that we do our operations in. So for this program, I'm going to start by loading D. Remember that puts the value D into our accumulator. Next, I will add C so that the accumulator contains D plus C. Now I can divide by E, giving me a value in the accumulator of D plus C divided by E. So this is that portion of the expression, but now we need to save this somewhere temporarily. I will choose to store it in Y. And the reason I needed to store that in Y was so I could put a different value in the accumulator. Specifically, I'm going to load A. Having loaded A, I can now multiply that by B. So I have A times B in the accumulator, and in Y I have this portion of the expression. I want to subtract this from A times B, so I will do a subtract operation here, which stores in the accumulator that whole result there. So that is my result that I want, but it has to be in Y, so I will once again need to do a store operation at the end. And that completes the program with instructions using only one operand. So order played a very important role here, and I had to temporarily store intermediate results in one place so I could compute something else and then combine them back together at the end. Ordering is an even more complicated issue when using the stack with 0 operand instructions, as we'll see next. For this program, I'll illustrate the state of the stack as I make modifications to it. First, we'll need to push A and B onto the stack. After we've pushed those items on, the stack will look like this. Now I can execute multiply. After which point, we pop these off, and what does the stack look like? Well, it's a stack with a single element, and that single element is A times B. Next, I'll push on D and C, and after pushing those on, the stack will look like this. So the result A times B is still in the stack, but D and C are now on top of it. And remember that all of the 0 operand operations that we can use only deal with the top two elements of the stack. So next I will do add, which will pop the C and the D off, add them together, and put the result back on, giving us a stack that looks like this. So the stack now has 2 elements on it, and I will push on another E. In order to compute this portion of the expression, I want to have D plus C quantity divided by E, so I can do a div instruction next. That pops these 2 items off, and I'll illustrate this here. D plus C is popped off there, and then E is here. I do the division, and this result goes back onto the stack, so that the final result of all of that will look like this. Now the stack has only 2 items on it again. The next operation I'll do is subtract. That pops this item off and this item off. And notice that this result is the final result we want to calculate. So after doing the subtraction, the result we want is the one and only element on the stack. Because these 2 elements were popped off, this will go back on the stack. And so after all of these operations, the only thing left that we need to do to save the result in Y is do a pop Y. And that completes our program with 0 operands. Once again, order was very important. The program was fairly complicated. However, all the individual instructions were very short. So that's the trade-off. When you have many operands in your instructions, you can do more with fewer instructions, but the size of all the instructions is larger, and it takes more processor work to process and deal with those instructions. When your instructions have fewer operands, your individual instructions can be smaller, and although the program will consist of more instructions, because of their simplicity, the processor can generally do all of those instructions very quickly. We'll learn more about this distinction as we eventually learn about CISC and RISC architectures in later videos.